So we're starting the notes on section 6.2, which is graphing advanced rational functions, so slightly more complicated than the ones that we've already done. So up here in this blank space on your notes, we're going to put in some of the things that you need to do, and we might come back to this space and put more things in here. But the first thing we're going to do is look at this new parent graph. So this is a simple version of what we're going to call inverse square function, because there's x squared there. So like we did with our previous rational functions, the simple ones we did the other day, the first thing that we're going to do is find the values where the denominator is 0, because that will be undefined because you can't divide by 0. So if I set the denominator equal to 0, x squared equals 0, and solve, I would take the square root of both sides, plus or minus, except it's a 0, so I'm just going to get x equals 0. So it's actually, the domain restriction is that x cannot equal 0. It turns out, just like in our previous rational function, that that's an asymptote. So there's a vertical asymptote at x equals 0. And there's a horizontal asymptote at y equals 0, which we'll talk about why that is in a few minutes. So I'm going to put those asymptotes here. This should look really familiar. So x equals 0 is a vertical line through 0. Y equals 0 is a horizontal line through 0. And then we get a similar shape to the previous types of rational functions, but not exactly the same. I'm trying to turn the light on this and I can't. Okay. So we get a curve in the upper right like we did on the previous ones, and it heads towards the asymptotes just like it has before, so we get something like this. And the thing that's different about this one is that our other curve is going to be in the top left instead of being in the bottom left, but it approaches the asymptotes just like before. So how are we going to know what the horizontal and vertical asymptotes are when it's more complex? So if you have something of the form y equals 1 over x minus h squared plus k, x equals h, just like before, is the vertical asymptote, and the horizontal asymptote is y equals k, which in this case there wasn't anything added, so it was 0. So that's the general shape. So we're going to use this. So notice the first thing that we did here was find domain restrictions. So domain, meaning what it cannot be, restrictions. So you do that by you set the denominator equal to 0 and solve. All right. So we're going to turn the page and do our first example. So we are going to eventually get to something that looks like this, but not in our first example. So here's the first example. So just like in the previous thing, we are going to want to find our domain restrictions. So we would set the denominator equal to 0. But why don't we factor it first? So the first thing we're going to do is factor the denominator. And I'm going to, at the same time, put it back in the denominator. So I'm going to write the factored form down here. So this one is relatively simple. So it factors into x minus 1, x plus 6. So I factored the denominator. And now, just like we talked about, we're going to set the denominator equal to 0. So x minus 1 times x plus 6 equals 0. Set each factor equal to 0. So this gives me x equals 1, but it's actually x cannot equal 1 because the denominator cannot be 0. And x equals negative 6, so again it's actually x cannot be 6. So the domain is x such that it is not 1 and not 6. So let's go back up here and look at this expression. We can simplify this because x minus 6 is a factor of the numerator and a factor of the denominator, so anything divided by itself is 1. So this simplifies to 1 over x minus 1. So once we're done with this problem, we're going to remember to go back to the front page and tell ourselves that we can cancel or simplify factors that are common to the numerator and the denominator. So since this simplifies to this function, our graph is going to look just like the graph of this function, which we know how to do, with the one exception that since this factor canceled, when x is -6, we cannot have a value there. So that is going to be called a removable discontinuity. So we get a removable discontinuity, and I'm going to start calling it a hole because it looks like a hole, which you'll see in a minute. And it occurs at x equals -6 because that canceled. So I want to find out what the coordinates are of that hole so I can put a hole there. So we're going to plug x, what was -6, equals -6 into the simplified function. So it's simplified to that. So I'm going to plug -6 in there. 1 over -6 minus 1. So that's 1 over -7 so my hole is going to be at the point x was -6 and y is -1/7. So I'm going to put that on the graph. So I go to -6, 3, 4, 5, 6, and -1/7 is really small. I'm going to draw a gigantic hole though so I can see it. And now I'm going to start graphing the simplified function. So I'm going to graph the simplified function. Y equals 1 over x minus 1. So I could write in the plus 0 so I remember what k is. So I have a horizontal asymptote at y equals 0. And I have a vertical asymptote at x equals 1, because that's sorry. And so I'm going to draw those in. So horizontal asymptote at 0, and a vertical asymptote at 1. And my a is 1, so I know where my curve goes, and it has the same shape that we expect, but we jump over that hole. That's literally a hole in the graph. You could fall through the hole. And then my other curve is in the upper right. So we're done with that. Now we're going to go back and put on the front page about removable discontinuities. So next thing we want to remind ourselves is we can simplify the function if a factor cancels across the numerator and denominator. If so, we get, I'm going to write RD for removable discontinuity, but I'm going to talk about it like it's a hole, because that's what it looks like. And we find the y coordinate of the hole by plugging the x into the simplified version. All right. And then the next thing that we did was we graphed the simplified version. I think that's going to be it for the front page. So we've got a few more examples here. So now let's look at this example. This time I have a numerator that's more complicated and a denominator that's simple. So I'm going to factor the numerator. So you should either use the box method or the grouping method. So notice there's a leading coefficient that's bigger than 1 and it doesn't factor out. So I'm looking for numbers that multiply to 2 times 12, so 24, and add to negative 11. I'm going to jump over the part where we do that work, and I'm going to tell you that it factors into x minus 4, the numerator, times 2x minus 3. So you can do the work if you want to verify that that's what the numerator factors into. And the denominator was x minus 4. So let's talk about domain. Anytime the denominator equals 0, that is something that's excluded from the domain. So let's set the denominator equal to 0, and that tells me that x cannot be 4. So the domain is x such that x is not 4. And now let's look, does this simplify? I have a factor of x minus 4 in the numerator and the same factor in the denominator. So those divide and give me 1, and my whole thing simplifies to 2x minus 3. So since that factor canceled, I have a removable discontinuity, a whole, at x equals 4, because I set that factor equal to 0. So I plug in 4 into the simplified version to find the y-coordinate. So my simplified version is 2x minus 3. So I have y equals 2 times 4 minus 3. So that would be 8 minus 3, which is 5. So that means my whole is at 4, 5. So I'm going to put that on here. 2, 4, 1, 2, 3, 4, 5. Whole. The whole's actually not gigantic, but I want us to be able to see it. And then I go ahead and graph the simplified version. So I'm going to graph y equals 2x minus 3. So that's a simple line. So the slope is 2, and the y-intercept is negative 3. So negative 3, slope is 2, up 2 over 1, up 2 over 1, up 2 over 1. I don't need that many, but up 2 over 1, I see that I do land on the whole. So I get everything along that line except for the whole. And we're done. And then we got another example. Here we go. So let's look at this one. So I have a numerator that's kind of complicated, and it's cubic. And we could write the p's and q's, so find the rational roots and try them. Or you could plug in some things, or you could graph it on your graphing calculator, or you could try grouping. Turns out grouping is probably going to work, so we're going to try to factor the numerator by grouping. So if I group it x to the third minus 4x squared minus 4x plus 16 groups, and then factor out the common factor, and the common factor here is negative 4. And then these match, so it works. So x minus 4 times x squared minus 4. So that factors into x plus 2 times x minus 2 because it's the difference of squares. Great, we factored it. And now I'm going to put it back here in factored form. So the denominator was x plus 2. So at this point, I'm going to check for domain restrictions. So the domain is everything except where x is equal to 0. So x plus 2 cannot equal 0, so x cannot equal negative 2. So x such that x is not negative 2. And now let's see if anything cancels. X plus 2 and x plus 2 are factors that cancel. So what I'm left with is y equals x minus 4 times x minus 2. So that is a parabola. And if you wanted to multiply it out, you would get x squared minus 6x plus 8. So the y-intercept is 8. I'm going to graph this in a second. And the vertex is negative b over 2 times a, so 3. And if you plug it in, you get y equals 3 squared minus 6 times 3 plus 8. So y equals negative 1. And then I have to check for my removable discontinuity here, so my whole. So my whole occurred when x was negative 2. So I plug the negative 2 into the simplified version. So that would be negative 2 squared minus 6 times negative 2 plus 8. And that turns out to be positive 24. So my whole is at negative 224. So I'm ready to graph. And clearly that's too big to fit. So I'm going to count by 2's on the y-axis. So I'm going to put my whole in there first. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this is 24. So at negative 224, I get a whole. So that's at negative 224. And then I've got a parabola with a vertex. Oh, I should have written this as in vertex form. The vertex is 3, negative 1. So I get 3, negative 1. Remember, I'm counting by 2, so that's 3, negative 1. And the y-intercept is 8, 2, 4, 6, 8. So that's 8. And now that's enough. I'm just remembering that it's symmetrical. And it looks like that. Fabulous. One more. Here we go. So, same thing. We want to factor the denominator because that's the thing that's complicated. So we want to factor the denominator. So I'm going to have to do my P over Q's, I think. So my rational roots. So I get plus or minus 1 for the 45. Plus or minus 3, plus or minus 9, plus or minus, oh, I missed 5, plus or minus 15, and plus or minus 45. To save myself time, I checked earlier, so I'm going to try 3. So I'm going to do synthetic division. 1, negative 11, 39, negative 45, and then I'm going to try 3. Bring down the 1. Multiply, add, multiply, add, multiply, add. Fabulous, it worked. So I am left with x squared minus 8x plus 15. And what I factored out was x minus 3. It's always the opposite sign inside the factor. This factor is more. It's relatively simple. So this would be x minus 3 times x minus 5, and I still had this factor of x minus 3. So that's the denominator. I didn't leave myself room to put something above it, so my function is x minus 5 was in the numerator, and now I have x minus 3 times x minus 3 times x minus 5. Let's do the domain first. So the domain restrictions are x cannot equal 3, set that factor equal to 0, likewise for that, and x cannot equal 5 when I set that factor equal to 0, so x cannot be 5, so x such that x is not 3 and x is not 5. So now let's see if anything cancels. X minus 5 and x minus 5 simplify, so I'm left with f of x is equal to 1 as a placeholder over x minus 3 times x minus 3. So I can write that as 1 over x minus 3 squared. All right, now I am going to have a whole, a removable discontinuity. So whole when x is 5, because that factor canceled and corresponded to that x value. So I'm going to plug 5 into my simplified version. So that would give me y equals 1 over 5 minus 2 squared, which is 1 over 3 squared. Oh, that was a 3. I knew something looked wrong. That was a 3. It was never a 2. 1 over 2 squared. 5 minus 3 is 2. So 1/4. So my whole is at 5 1/4. That's my whole. All right, I'm ready to graph. So I'm going to put my whole on there. 1, 2, 3, 4, 5, 1/4. So that's my hole. And now, what is this? This is just like the one we did on the very front. This is inverse squares function, inverse square function, because 1 over something squared. So my h value is 3, and my k value is 0 because there's nothing added over here. So that tells me that I'm going to have a vertical asymptote at x equals 3, my h value, and a horizontal asymptote at y equals 0, because that's my k value. So now I'm going to draw in those asymptotes. So I have a horizontal asymptote at 0 and a vertical asymptote at 3. 1, 2, 3. So here. And remember, with our inverse squares, we get the same curves as in the other kinds of rational functions, but they go in the top 2 quadrants. So I get one here, and I get one here, and it touches and then like jumps over the hole, and we're done.